Aaron, and Michael, and Hannah for organizing this workshop. It's really been a lot of fun so far. I'm looking forward to the rest of it today. So I'm going to talk a little bit about human multi-robot collaborative manipulation. But first, and I know that Alessandra's going to tell you later, but I'll give you a preview. There's going to be an upcoming call for papers for special issue on impact-aware robotics in the IEEE transactions robotics. So I'll temporarily wear my transactions and robotics hat and ask you all to look out for that, because this is exactly the target group who would be submitting to this special issue. So I want to start talking a little bit about the Center for Robotics and Biosystems, because we relatively recently launched at Northwestern. The CRB is faculty from, well, some of them you can see listed here, and the faculty come from a lot of different units at Northwestern. And in particular, we have a strong connection with the Shirley Ryan Ability Lab and the medical school. And that's one of the motivations for talking about human robot systems today that I'll get to in just a moment. But research in the Center for Robotics and Biosystems covers bioinspiration, neuromechanics, and neuroscience. I saw some work by Mitra Hartman here, for example, a little earlier. That's what you see represented in this figure. Human machine systems, we do a lot in human robot systems, and that's going to be the focus of most of the talk today. Swarm robotics and decentralized computation. Soft robotics, a relatively new area for us, but one that we're growing in. And general autonomous robotics, which is kind of a grab-all for everything else that we do. And in fact, when I was Aaron first invited me to this workshop, I thought I was going to be talking more about our work in robot manipulation. And in particular, you can think of this as yet another optical tactile sensor. Ours is called the VisiFlex, and we developed it so that we could get really good wrench sensing at the fingertip contacts. Okay. So one thing you can see here, and I guess the people online can't see me pointing, so I'll point here with the mouse. We've got a steel flexure built into the sensor. And a nice thing about spring steel is that there's very little hysteresis or creep. So you're not dealing with 3D printed materials or elastomers or other things. So you get really good, displacement to force readings. And so what we have here is a camera looking from below that watches the deflections of the fingertip. And from that, and knowing the stiffness of that flexure, we can get the 6 degree of freedom wrench at the contact. And we can also do visual, it's not shown here, we can do visual recognition of the contact. So some advantage of this is a rounded surface for rolling contacts. Manipulation involves rolling, well-characterized compliance that doesn't suffer from hysteresis or other sort of elastomer effects. But actually, I decided not to talk about that because just 3 days ago, we submitted a paper and a video on our latest work on human robot manipulation. So I want to spend some time talking about that. It's kind of hot off the presses. So this is an example of human machine systems. And in particular, I want to talk about human multi-robot mobile manipulation. So this is one or possibly more humans interacting with a team of mobile manipulators to manipulate objects that are large. So I'll call it a payload. The payload is large, possibly heavy, but at least large. And it's advantageous to have multiple points of contact. So you could imagine having, well, if there's one large object, you have one large robot doing all the manipulation for you. But if that object or that payload is fragile, you don't want all the contact at one location because of high stress concentration, right? You'd like to distribute the contacts over the payload. Or maybe the payload has high degrees of freedom, either because it's flexible or because it has internal joints. And to control those degrees of freedom, you need more contacts distributed over the object. The third characteristic we're interested in are tasks that are not easy to automate, maybe because you're doing it one time, maybe because you need the flexibility of a human involved to provide the situational awareness and sensing capability for the one-off task. So we're thinking about construction, warehouse, factory automation, or factory tasks that are described by these three characteristics. And the robot system that I'm talking about today, these nnid mobile cobots, are also useful for autonomous manipulation. But today I'm going to focus on the human-robot interaction piece of it. Okay, so this is just a quick video demonstrating some of the capabilities of the system. So here it is, Matt Elwin is transporting this a 15 kilogram payload with the assistance of the robots providing float mode. Here it is where we are experimenting with its ability to provide weightlessness so that the human is feeling like the object is just in zero gravity. Here's an assembly task. We're inserting these two pipes into a fixture, 6-degree freedom assembly task. And this is an example of an articulated object. So this, is two bodies connected by a hinge joint. So total it has 7 degrees of freedom and two humans manipulating it. And I apologize for those of you in person, because you're watching it over Zoom. The video is kind of jerky. If you watched it live on my computer, you'd see it a lot smoother. And I don't know if there's anything that we should do to try to change that. But okay, so let's talk about that. So obviously there's been quite a few systems where multi-robots are manipulating a single object, and I've chosen this one. Nice work by Hirsch's group. And so these are 3 omnidirectional mobile bases, mecanum wheels, with these Panda robot arms attached to them. They're rigidly grasping a rigid object, and they're moving together to cause a coordinated motion of the object. So we can think about, how do you model 3 robots grabbing a common payload? Well, first I'm going to assume that the payload is described by a finite number of degrees of freedom, so it's not sort of infinitely deformable. And so I'm going to call the payload configuration Q sub P, so some set of generalized coordinates that tell me where the payload is, and where the robots are is Q sub R. So this, whatever number of degrees of freedom, so I guess maybe 3 for the mobile base, 6 or more for the Panda, and that's going to be, or 7 or more for the Panda, and that's going to be the degrees of freedom for each robot, and you put them all together and you get this Q. And then of course, the full configuration is going to have constraints. So once you're grabbing onto a common payload, there's going to be closed loop constraints. So those are configuration constraints. And for instance, the wheels of the robot are traditional wheels, not these omnidirectional mecanum wheels. Then you might have non-holonomic constraints. So put all of that stuff together, take the derivatives of the closed loop constraints, and you can use this sort of standard modeling approach here, where you've got inertial terms, velocity product terms, potential terms is equal to the control. So this U of Q is your feedback control. S of Q tells you how those controls map to the variables of the configuration. And then you've got these constraint forces. So the constraint forces here, so these are down here, these are the constraints, including the closed loop constraints and any non-holonomic constraints. And these constraint forces, these Lagrange multipliers, are the things that make sure that the constraints are satisfied throughout the manipulation. So that includes constraints due to the grasps. Okay, so you can think of the contact forces of the robots on the payload as being encoded in this lambda here. One thing to notice, though, is that all of the terms in these dynamics are actual dynamics, actual mechanical dynamics, except for this one. U of Q here, that's an active feedback controller. So you're interrogating the configuration of the payload and the robots, and you're deciding what forces to apply to the robot joints or to the wheels to control the motion. So feedback control is going to be subject to latency, right? Maybe that loop is running at 1,000 hertz. If you're doing network control, so the robots are talking to each other over Wi-Fi, or maybe they're talking to a base station, there's going to be additional latencies and minimum or reductions in bandwidth. And then if the motors themselves have frictions and transmissions and things like that, the quality of U of Q is much less than the rest. All the rest are happening at every frequency, all bandwidths, right? U of Q is a little bit different. So what does that mean? That means that even for these Panda robots, which are pretty good at impedance control, they're still implementing it in with latency and finite bandwidth, right? So if there's a misconfiguration, if there's a motion incompatibility of the Panda arms, it has to be taken up by something, right? Either the object has to flex, or the robots can't move the way that you ask them to, but there's going to be something, some mechanical compliance that usually isn't well characterized. So what I want to talk about is what we think are requirements for a team of mobile cobots, or MoCobots for short. So first of all, we think that passive compliance is required. So we have to build in the compliance into the mobile manipulators themselves and not expect the payload to give them to us. So we need passive compliance to accommodate transients over constraint, so as not to damage the payload itself or possibly the robots. We want manipulability of the payload, so we want to be able to control all the degrees of freedom of the payload. And we'd also like to have end-effector force control. So whatever the mobile base is doing, including if it's a tracked mobile base or a legged mobile base walking on slippery ground, we want the end effectors to be applying good force control. Okay? We want to somehow decouple all the sloppiness of the mobile base from what's happening at the end effector. So just expanding on those a little bit. So if we have passive compliance, so here's a generic mobile robot with an end effector, then we're going to assume that either because you're using series elastic actuators or variable stiffness actuators or direct drive or something, you're able to implement a passive compliance at the end effector that relates small changes in the configuration of the end effector to small changes in the force through this stiffness matrix K. So K sub I because I refers to the ith robot, and we're going to have n of them total. So if you think of n robots grasping a common object, an ellipsoid in this case, so we've got three robots grasping it, then you can talk about what's the effective stiffness seen in a frame of the object. And you can calculate that by just doing some matrix transformations here. And now you've got the effective stiffness of the object due to the contributions of each of the three end effectors. So things you have to think about. First of all, if you want to have safety to end effector disturbances, say this end effector here gets displaced by a couple centimeters, and you want to make sure that the object is not damaged by that displacement, then what you want is a maximum eigenvalue on the stiffness at each individual manipulator. If you want safety to external disturbances, so maybe it bumps into a person, right? The payload that's being carried bumps into a person, and I don't want that to feel to the person as a very rigid contact, then you want to have a maximum eigenvalue on the total stiffness of the grasped payload. And finally, for motion control performance, you might want to have a minimum eigenvalue. So if you have very sloppy, loose, passive compliance, it's very difficult to do high bandwidth motion control. So that's passive compliance. Next is manipulability. So again, we have the configuration of the payload in the robots. And I'm going to say that the degrees of freedom of the payload is 6, because that's a rigid body, plus any internal degrees of freedom D. Okay, so in this example you see here, there's 1 internal degree of freedom, so the total degrees of freedom of the payload is 7. So these are our dynamics from before. If you eliminate the Lagrange multipliers, you can write the second order, second derivative of the configuration as a function of the control inputs U and this drift term here, and then this matrix F. And F you can calculate like that. So now we've gotten rid of the Lagrange multipliers. We see how the controls map to the accelerations of the payload. We can write that F matrix so that it has a portion. The top half corresponds to the payload. The bottom half corresponds to the robots. And then you say that the manipulability of the object that you're manipulating is just the rank of that matrix. So how many degrees of freedom of the payload can I control instantaneously? And then we can say that the payload is fully manipulable if the rank of that submatrix is equal to the number of degrees of freedom of the payload. And then finally, we want to be able to do end effector force control. And the condition here is that when we're designing our control laws for collaborative manipulation later, I want to be able to abstract away from a particular robot. And the way I can do that is if I assume that the end effector is giving me good force control, regardless of all the stuff that's happening at the mobile base. So if we have high fidelity manipulator force control with a large enough workspace, so the manipulator has a large enough workspace to accommodate sloppy motions of the mobile base, then we could do things like legged outdoor robots, wheeled skid steered robots, tracked robots, and all of these things could implement the sorts of collaborative manipulation that I'll be showing here. Okay, so I'm going to talk specifically about our mobile collaborative robot, the nnid. So it's got an omnidirectional cannon wheel mobile base. We're using it for indoor experiments. It's got a delta parallel manipulator, so it has 3 degrees of freedom. All the actuators are here at the base. And each of those actuators is a series elastic actuator, and that's where we're getting the passive elasticity from. And then finally, we have an encoder instrumented 3-degree of freedom passive gimbal wrist that actually does the grasping of the object, of the payload. There's no gripper here. When we do our experiments, we're attaching the payload to the robots. That's not a problem that we're concerned with here. We're more interested in how to design the control laws to collaboratively manipulate with a human. So the way you can think of it is that each omnid applies an arbitrary 3D linear force through its gimbal center. Because that gimbal is passively rotating, we can't support any torques about it. So each robot ends up looking to the payload just like a 3D force through a point. Okay, so this is just a video of the robot sort of showing the motions that it's capable of. 3 degrees of freedom controlled at the mobile base, 3 degrees of freedom controlled at the delta, and then 3 passive freedoms. You can kind of see the gimbal wrist flopping around. So the delta parallel manipulator has got a proximal link here and the distal linkage that keeps the end effector always parallel to the base plate. And then the series elastic actuator, we're kind of zooming in on the mechanism here. The series elastic actuator consists of a motor driving a pulley with a 12-to-7 reduction, and then 2 antagonistic springs that pull on the proximal joint that you see here. And those springs are pre-tensioned. And so if we want to create forces at the joint, then we just move the actuated yoke and it pulls on the proximal link through the springs. So this is just a video of the link here. The proximal link of the delta is fixed. And so as the manipulator moves back and forth, you're applying different forces at the end effector, which is constant in space. Okay, so going back to the 3 things we need: passive compliance, manipulability, and good force control at the end effector. The passive compliance we get from the SEA is very linear. So it's about 60 Newton meters per radian. You can see experimental data plotted on top of the theoretical fit. So we're getting the passive compliance from the SEAs. This is a lot of stuff on the performance of the manipulator, but we can just focus in on this part. We're getting a linear stiffness at the home position. So the robot's here shown at its home position of about 1,400 newtons per meter in the horizontal directions and 2,000 newton per meter in the vertical direction. And as the configuration changes, that stiffness will change some too. Okay? It's configuration dependent. And then the workspace volume is about about that big, right? About 30 centimeters or so in diameter. So going to manipulability, as I mentioned, each omnid is acting like a source of a point force. And so if you have 1 robot, then you can have a manipulability of 3. If you have 2, then you have a manipulability of 5, right? So if I have 2 points of force here, there's no way to resist the torque about the line that's connecting them. So it's just kind of like a grasp problem. But if I have 3 omnids involved and they're not all collinear, they're not all lying on the same line, then I can control up to 9 degrees of freedom of a payload that has internal degrees of freedom, or at least 6 for any rigid body payload. And then finally, we need good end effector force control. This is just a little bit of the experimental results of using the SEAs. So here, the SEA is doing a step response of 5 Newton meters, and the settling time is less than 0.1 seconds. And that's also reflected in the frequency response, where the crossover frequency or the bandwidth is about 20 or 30 hertz. And so that's the kind of force control capability that we're getting at the end effector. So the controller itself is basically broken into 2 pieces. One is for the manipulator, one is for the mobile base. The manipulator, like I said, is a force controller. So it's going to be sensing the configuration of the manipulator and then providing a force. And then optionally, it might also be able to sense the configuration of the payload. That's these dotted lines, as well as the configuration of the base. But most manipulation demos that I'll be showing you here just need to know where the manipulator is. And the mobile base is going to be sensing also where the manipulator is, but could also be sensing where the mobile base is depending on the control mode. If the robots are talking to each other, and our robots they can form a mesh network, or they can all talk to a central base station. Then there's also external communication that's influencing those controllers. But I'm not going to talk about any controllers that use that in this talk. So example controllers that you could run on the manipulator include just locking the actuators. If you just lock the actuators, then you just have a three-dimensional spring on the end of the robot. You can do gravity compensation, and this is very useful. And also manipulator plus payload gravity compensation. And then all the usual force, motion, and impedance control. And for the mobile base controllers, here's an important one that we use a lot is called recentering control. So the job of recentering control is for the mobile base just to move to keep the robot arm inside its workspace, right? It just wants to always maximize how much room it's got to move so that we can meet this condition 3 that I mentioned earlier, that we get good force control at the end effector. So recentering control, you can do trajectory control, and then in some cases it might be useful to do a combination of the two. So this is a convex combination where depending on alpha, how you choose it, you're either just doing recentering control or just doing trajectory control or something in between. So this is a video showing the natural stiffness, the passive compliance of the end of the robot. So this is with the actuators locked. And so then if you actively control the stiffness at the end effector, then you can increase it or lower it. And so this is a case where we've actively controlled the SEAs to provide a lower stiffness at the end effector. Of course, the key difference is that's happening with a 20 or 30 hertz bandwidth, whereas the locked actuator motion, that's applicable at all frequencies. This is the walk the dog mode. So here, what the robot is doing is it's doing gravity compensation of the manipulator so the user doesn't have to support it. And it's applying 0 forces in the horizontal directions. So now the user can just grab onto the end effector and pull the robot around, and the mobile base is just trying to recenter itself to keep the manipulator in the center of its workspace. And you can notice at times that sometimes the manipulator is not at the center of its workspace, and that's because the mobile base control is not as good as the end effector force control. So it's trying to catch up. And if you can imagine that you had like a walking robot on rough ground outside, that play there is something that you need to be able to get good end effector force control. Okay, so multi-omnid behaviors. So now what can we do when we have several of them working together? We define 2 classes. One is emergent behaviors, and the other is coordinated behaviors. So emergent behaviors are happening only with mechanical communication. So the human is communicating with the robots mechanically through the payload. The robots are communicating with themselves mechanically through the payload. Coordinated behavior includes wireless communication between the robots. And I'm not going to talk about any of the behaviors that we can get that way today. So this video is showing a payload float mode where the robots are just trying to make the object feel like it's in 0 gravity. So it floats freely, and the only forces that the user needs to apply are the ones that are necessary to accelerate it due to the inertia of the object. So this payload weighs about 15 kilograms, and the maximum payload of each robot itself is about 9 kilograms. So you need more than one to just be able to support payload. And so here's an example where a human working with the robots can solve an assembly task. So again, very light forces by the human, and very intuitive because you're interacting haptically as opposed to trying to teleoperate. Right? Teleoperation is much more difficult, but haptically the motion is completely intuitive. And then this is just an example of a 7-degree of freedom payload with 2 humans manipulating it. Here, the payload compensation is a little bit different because the robots without inter-robot communication don't know where the other robots are. And so they can't perfectly cancel gravity like they could with the rigid object. And so that's something that becomes possible when the robots talk. This is the singularity I mentioned earlier. If you get all 3 wrists into a line, then they can't resist the torque. And so the humans have to provide that torque about the line. Okay, so conclusions. So our initial experiments show that these 3 robots make it very easy for a single human to manipulate multiple objects simultaneously, or sorry, a large object with the help of the robots. But things we want to study in the future include empirical study of the benefits of haptic interaction versus teleoperation. So I think it's much easier to grab onto the object and pull it around than it is to try to drive it around with a joystick. But how much easier? Coordinated control. So now we're using the wireless communication between the robots to do things like implement safety filters, human intent estimation, and skill transfer. So eventually we might want to automate these experiments, right? So how does a human teach the robots, and the robots learn from what the human is doing so that they can do the same thing in an automated way in the future? And then finally, it's just autonomous manipulation with no humans involved. And now you can imagine having the robots grab onto the payload, shaking it around a little bit, figuring out what its kinematics are, what its inertial properties are, and then using that for dexterous manipulation. And so with that, I'd like to conclude. Thank you for your attention.
I think we'll take 1 or 2 questions now, just so we have time for the panel as well. You can ask kind of questions then as well. Questions?
Yeah, so the mobile-based controllers that I showed in this talk are really simple. So everything I showed, they're essentially doing recentering. So they're seeing what the manipulator arm is doing, and then they're moving to try to get underneath it. So that's just a simple PID controller to try to zero out the manipulator's end-effector coordinates. Does that answer your question? There's certainly other things that you could do, but what I showed here, that was it. Yeah. So the other question was, how is the motion of the manipulator base used by, or sorry, the base used by the manipulator controller? It's not. So if you looked at the control algorithm, control block diagram I showed earlier, the manipulator is only looking at the manipulator's configuration. It's not looking at what the mobile base is doing for all the control laws I showed today. But there are other cases where you can imagine they should be coordinated. But right now, the manipulator is trying to do what it wants to do, and the mobile base's job is just to help it do that. Sure.
1 more question.
Thanks for your talk. I was wondering if you ever wanted to add any kind of planning kind of above the control that you have, and if the elasticity makes that easier or harder.
So definitely. So what I'm showing you today is what we think is an enabling platform to do lots of research, right? So there's a little bit, but there wasn't a whole lot of research in what I'm showing you here today. What it's mostly is development. And so, yeah, eventually we want to be able to, add our decentralized controllers and our planning algorithm on top of this to be able to do things like compliant manipulation. So we're always going to have compliance, and we're thinking about compliance in contact cases. So it's going to help us. If you're thinking about doing, an insertion task, for example, the remote center of compliance idea is an old one, but the idea there is that the end effectors would be creating a remote center inside of the space you're trying to apply or trying to insert into that essentially pulls the manipulator into that. So yes, these are all things that we want to do in the future.
All right. And let's thank Kevin one more time.
Thanks.